Hello, my name is Ian Burkak, and today I'll be sharing with you guys my presentation on analysis of knee x-rays with deep learning. So the knees are probably the most important joint in the human body because it helps you move around and helps you bear weight every single day. So when you suffer an injury with your knee, it can have devastating consequences on the efficiency and easiness of everyday life. As someone that has torn his ACL in the past, and I still feel the effects today of like not having good knees to be able to do everyday function. However, one of the big advances in medical research has been the use of neural networks to be able to classify and detect injuries, in this case with the knees, to be able to produce accurate diagnoses. With that being said, there are some issues with current solutions to be able to do medical classification. Mainly, it's tough to obtain large and diverse data sets, and that is primarily due to medical privacy rights, where you have to ask for consent from the patient to be able to share medical information, and that is generally not an easy task. When you combine it with the fact that current existing pre-trained medical imaging classification models are very complex, it is very easy to overfit in a model. So as a result, I am proposing a solution that will build, train, and fine-tune multiple neural networks to find an optimal solution that trains quickly without sacrificing the accuracy. We'll also implement regularization techniques to prevent overfitting. So for my model demonstration, I built three different types of models. The first is a simple convolutional neural network. So what we see in the top confusion matrix, which is basically a prediction of the classification output of the neural network compared to the true label and the training loss plot. So in the training loss plot, we should expect to see a consistent decrease, and because that will indicate the model is learning, which that happens in this plot. However, there were issues with the simple convolutional neural network, mainly in its inability to classify grade 1 tears and its tendency to default to no injury or the normal label. So it was still a good accuracy of 65% and a good training time of 10 minutes. However, this model can be improved. So I then built from scratch a MedNet model, which is a much more complex model consisting of 44 layers of fine tuning. The training time for this, however, took a lot longer than it should. It took an hour and 10 minutes. However, it does classify data a little bit better while maintaining the same accuracy. However, when we look at the training and validation loss plot, we see that there is an evidence of overfitting. We're not getting that decrease that we thought we would have, and there's a lot of noise, particularly in the validation loss curve. As a result, the model is overfitting. Therefore, we need to decrease the number of parameters and create a simplified MedNet model. So for the simplified MedNet model, we took out some of the layers and we added early stopping. Early stopping is a mechanism that allows the model to stop training when the validation loss does not improve after a certain amount of time. So, and actually, when we look at the training and validation loss, it stops at around epoch 32, which completely cuts the training time to about 5 minutes, which is even faster than the simple convolutional neural network. However, it didn't fare as much. It didn't do too much differently from the MedNet model in terms of classification, but when we combine the training time of the simple convolutional neural network with the better classification of the MedNet model, we have produced a model that actually gets the best of both worlds. So in summary, simplifying complex pre-trained models can lead to more efficient training while minimizing potential accuracy loss. And the model size should indeed reflect the data size. Otherwise, neural network models can be prone to over and underfitting. And I'd like to thank you guys for coming to this presentation day. And please let me know if you have any questions. Bye-bye.